what we'll do today is try to develop the formal theory a little bit. But before we do that, I wanted to mention something about inelastic scattering. So scattering where some of your probability disappears into some other states. So, I mean, the idea is, of course, what is inelastic scattering? It's really, in our usual setup, for elastic scattering, you have some free state that comes in, free particle state, and another one that comes out, and no energy is lost in the process. And so you start with a free particle state with some momentum, and then another free particle state that comes out with the same magnitude for the momentum. The only thing that happens is that it can change directions, but the energy is conserved. And so, in some sense, if we think about the target as being in some state, the target just remains in that same state after the scattering. And what inelastic scattering represents is when something changes and some energy is absorbed by the target, right? And so then when the outgoing particle comes out, you lose some energy. So that's the idea. And so there's actually a way we can think about it if we recall some facts that we've derived for elastic scattering. Namely, remember that the partial wave contribution to the scattering amplitude is related to the S matrix as follows. And we'll talk more about the S matrix later. And remember that, the scattering amplitude then we can write as sum over L for spherically symmetric scattering potential, so that the scattering guy only depends on the angle between the incoming and outgoing beams. This is what it looks like. Again, got these Legendre polynomials. So, okay, that's the scattering amplitude. And so for elastic scattering, we know that the total cross-section is just, you integrate up this, scattering amplitude, the square of it. And you get pi over k squared from the angular integrations and so on. There's 2 pi from the integration over phi. You can then use properties of the Legendre polynomials to do the rest of it. And what you end up getting is, and you'll practice some of these kinds of integrations on the next homework. So it's just, you're left with this SL minus 1 quantity squared. So then, and that's elastic scattering. And again, in elastic scattering, all of the energy that comes in is equal to the energy that comes out. So an inelastic process, as I mentioned, is one in which something happens and some energy is absorbed. And so one way to think about it is, if we look at our target, which again, and we can put a kind of sphere around it far away, and we can ask, as we send in particles into here, how many go in versus how many go out. And we know in elastic scattering, the number that come in has to be equal to the number that go out. So for So the inelastic scattering cross-section must be given by the difference in the number of particles that come in minus the number of particles that come out, divided by the flux. If you go back to the definition of the scattering cross-section, that's sort of that's what we have. So we can actually calculate some of these things because we always know the number of particles that come in. We know that because we send in a plane wave. So, and it'll be convenient to look at the partial wave contribution to all these things. So we can actually look at the nth partial wave contribution to the inelastic scattering cross-section, and correspondingly the nth contribution to the number of particles. And I'll calculate that in a moment. But again, this guy would be, of course, sigma elastic, the nth contribution to the elastic cross-section from each partial wave. Each partial wave contributes some to the scattering cross-section and correspondingly to the number of particles in and out. So what is the number of particles that come in? We know we send in a plane wave. The incoming particles come in as a plane wave with some amplitude, say, along the z direction, say. So the number of particles that come in, the partial wave contribution, well, it just has to come from the partial wave expansion of the exponential, which we already looked at. And what you get is 2L plus 1 squared magnitude of A squared over 4K squared. You get 2 over 2L plus 1. That's from the expansion of the exponential and in the partial wave. This is the incoming velocity part, and then there's also a 2 pi factor coming from the integration over the phi direction. We're basically looking at the number of incoming particles at some far radius r due to this incoming plane wave. So of course you have to do a spherical integration and so on, and the nth partial mode will come from the expansion of this. You expand this, right, in incoming and outgoing spherical waves, and you just look at the incoming part of the spherical wave, and that lets you extract these factors here. And so the finding is that the number of particles coming in from that particular mode is just given by this guy. Okay, so what about the number of particles coming out? Remember that in the solution to the Schrodinger equation for scattering that included both the outgoing and incoming spherical waves, let me, I guess, write that down just to remind you. Remember that the full solution, which includes the incoming wave and all the stuff that gets scattered, that full solution in terms of the partial wave expansion had the form A, that amplitude, and then we had a sum, 0 to infinity, 2L plus 1 over 2I KR minus 1L here, and we had a minus 1L e to the 2I delta L. That's this S matrix. And this was proportional to the outgoing spherical wave. And then we had minus the incoming part, and this was all. So if we look at the sphere far away here, the stuff that's proportional to e to the minus IKR, that's the stuff that's coming in spherically, and this is the stuff coming out. But you see the only difference between these two factors is just the presence of this S matrix element. There's also this thing, but that's just you know, plus or minus 1. So when we compare the flux in and out, and we compare the square of the coefficients in front of this guy and this guy, the only difference is this S sub L. So yeah, you can actually kind of see where this part, the in part, is of course the square in front of this coefficient, so you can sort of see where some of these factors come from, like the 2L plus 1 squared and the K squared. So and you can work out the rest. So okay, so the only difference then between the incoming and outgoing is this S sub L. So the number of particles going out in that Lth partial wave must just be equal to the number coming in times the magnitude of S sub L squared, right? Because that's the only difference. So, okay, and this kind of makes sense, right? Because for elastic scattering, S sub L is just a phase factor, so its magnitude squared is always 1. And then, you know, for elastic scattering, the number of stuff that comes in equals the number of things that come out. And that makes perfect sense, because in elastic scattering, you should conserve the flux of particles. Everything that comes in just comes out as a free particle. So good. So this is what it is, and now we can actually just use this formula for the inelastic scattering cross section to figure out what it is. So the inelastic scattering cross section must be well, it must be the sum. Well, it must be the sum. It must be the same as the elastic scattering cross section, except you have 1 minus SL squared, because you can just use this formula, right? The number of stuff coming in minus the number of stuff coming out. That's 1 minus, that's number of stuff coming in divided by the flux, 1 minus the magnitude of S of L squared. So that's what it must be, just from using that formula. Again, the flux, so this is number of, we could do the rest of it. I can just show you the flux. So we have this formula for the number of incoming particles. We have the number of out particles, and then the only other thing you have to know is the flux, right? And the flux is just the rest of this stuff, right? It's well, let's go back. Let's see, make sure I get all the factors right. We derived the flux in the first lecture on scattering. For a plane wave. Just want to make sure I have it right. Yeah, the incoming flux is the magnitude of A squared. And then times the velocity, right? And the velocity is h bar k over m, the momentum over m. So, okay, so everything, so you can just, if you divide this, the a squared factors cancel out. You pick up another factor of k, so you get a 1 over k squared. The m's cancel and the h bars cancel, so you get a pi over k squared, which is this term out front, times 2l plus 1 times 1 minus SL squared, because that's the difference between the incoming and outgoing. So, okay, now we have all the factors. We have all the factors right, and so that's the result, is that the inelastic scattering cross-section is given by this guy, and then the other important thing to note is that the elastic cross-section, which we calculated before, is given by this. So those are the two important formulas that we need to understand both kinds of scattering. Any questions about that? Okay. So we have these two expressions, and now we should try to figure out what we can learn about. Oh, and again, so notice that if the magnitude of S of L is 1, which it is for just our elastic scattering solution here for the wave function, because it's just a phase, then this guy just vanishes and there's no inelastic scattering, right? The way you would get inelastic scattering, like by solving a Schrodinger equation, is you'd have to explicitly take into account like how the target absorbs energy through some change of its state, something like that. And then if you do that, then your solution for the wave function would no longer have this form, and this S of L would pick up, it wouldn't be just a phase like this. It would pick up some, the phase would pick up some imaginary components. And then what would happen is the magnitude of S would be less than 1. And then this would mean that you have some inelastic scattering. But we're talking generally for now. We don't know what the solution is to the wave function, but whatever it is, we know that these expressions have to be correct for the scattering cross sections. So let's look at the total cross section, which would be a combination. It's, you know, however the scattering occurs, it doesn't matter. The total cross section would be a combination of the two. And thankfully, these things are pretty easy to add. You just have that 2L plus 1, and then you have S of L magnitude, this guy, and you get the plus 1 minus S of L squared. So this is nice because we can start expanding this. And so this would be S of L minus 1 times S of L star minus 1. It's just a convenient way to represent the magnitude squared. Then you got the plus 1 minus magnitude of S of L squared. So some stuff will start to cancel. This is equal to 1 plus 1. This term, the minus 1 times minus 1, 1 plus 1. And you get a minus L sub L minus S sub L star. And then that's it, because the other the magnitude squares, they cancel. And this is equal to 2 minus twice the real part of S sub L. If you add a number to its complex conjugate, the imaginary parts vanish, and you just get left with the real part of that number. So all of this tells us that the total cross-section is actually given by one minus the real part of S sub L. And that's a very important formula. And you can start to see why in the theory of scattering, complex numbers start to play a very important role, because a lot of the properties of the scattering will depend very sensitively on the analytic properties of your solution, in particular the analytic properties of these S matrix elements. So this is a good formula. So if you have access to your S matrix elements, you can use them to calculate your cross sections, and this is the total cross section, including both elastic and inelastic scattering. And if we go back to the inelastic portion, again, what we're saying here is that there's some inelastic scattering if S sub L is different from 1. If S sub L is not equal to 1 or its magnitude is less than 1, then we'll get some inelastic scattering. But what's interesting is that if you look at the expression for the elastic scattering cross-section, right, there's no way to get this to vanish unless S sub L is equal to 1 identically, like without any phase. So that's very interesting. Quantum mechanics tells you that there's no way to actually get rid of elastic scattering in any kind of scattering problem. That's not true classically, because classically you could, for instance, send your particles into a target that completely absorbs all the particles. That would be an example of perfectly inelastic scattering where nothing comes out. But in quantum mechanics, you can't have that. You always see you can't make this vanish, right, while this is non-zero. Is what I'm saying here, because the only way that this is non-zero is if the magnitude of S sub L is less than 1. And the only way this is 0 is S sub L is identically equal to 1. So there's no way to kind of, you can of course make the magnitude equal to 1. So you can make this vanish, and then S sub L will just be some phase, but then this will be just, then the total cross section is just the elastic scattering cross section. So you can have perfectly elastic scattering, that's fine, but you can't do the reverse. You can't make this 0 and this non-zero. It's not possible. So that's kind of interesting. That's one thing that we learned from this. The other thing that you learn is that you can actually connect the total cross section. You see it depends on the real part of S sub L, and there's this 1 minus S type of thing. If we go back to the expression we had for the scattering amplitude, we see that the scattering amplitude also has this, S sub L minus 1 type of deal. So actually the total scattering cross section must be related to the scattering amplitude. The only difference here is we have this P of L cosine theta, That's a little bit annoying, but no big deal. We can just evaluate f at theta equals 0. And what's theta equals 0? That's just the that's when the angle between the outgoing and incoming directions is the same. So that means you look at forward scattering, things that just go out in the same direction. If you look at that, you get 2L plus 1 over 2IK, and you get the SL minus 1, and the PL evaluated at 1, its cosine is 0. Well, that's easy. That's just 1. And you get sum over L. And now we can break up the S into its real plus its imaginary part. And of course, there's a 1 over I. So this, I can multiply and divide by I, and I'll pick up a minus sign. And then what do I get? I get I times the real part of S sub L plus I imaginary part of S sub L minus I. Oh, sorry. There's no I. The I is, you get an I times I, which is a minus 1. This is the minus sign. So if we compare, here it's I times stuff, real part of S minus 1, and here it's the so if we compare, if we look at F, right, it'll have a real and imaginary part, and the imaginary part, that's all the stuff that's proportional to I, right? So the stuff that's proportional to I is the sum over L, 2L plus 1 over 2K. And if we multiply through by this minus sign, it's 1 minus the real part of S sub L. The other part is the real part of F. So, but the imaginary part is this. And if we compare these two things, right? If we look at the expression we got for the total scattering cross section, and we see that it must be related to the imaginary part of F. So sigma is equal to 4 pi over K. There's a factor of K difference and a factor of 4 pi here, because here's a 1 over 2, but here it's a 2 pi. 4 pi over K times the imaginary part of the scattering amplitude evaluated in the forward direction. Very important formula. This is called the optical theorem. And again, this hopefully shows you that the analytic properties of your solution to the Schrodinger equation for scattering, it'll have very important consequences for actual measurable quantities like the total scattering cross section for that problem. So this is just one example of the way in which analytic properties of, say, the scattering amplitude are related to a measurable quantity, but there are many more. And if we could probably have a whole class of based on scattering, quantum mechanical scattering. In fact, there's nice books about it. There's a book by Taylor. I think if you just Google Taylor and quantum mechanical scattering, you'll see that there's entire textbooks devoted to careful analysis of the analytic properties of these solutions. And it's a very rich field, but we're not going to spend that much time on it because we have to cover a lot of stuff. But if you're interested in this kind of stuff, there's a lot more to be said about it, especially about these analytic properties of the solutions. But this is good enough for us. You at least have some nice expressions here for the scattering cross sections, and we've derived the optical theorem, which is a very powerful result. And when you get to do like quantum field theory and things like this, you'll see that a lot of these results extend also to when you're doing the quantum mechanics of fields instead of particles like we're doing in this class, single particles. So yeah, that's what I wanted to say about that before. And so are there any questions before we jump to general methods, meaning we kind of started with an asymptotic solution to the Schrodinger equation, and I didn't really derive it or justify it very much. I just said, well, this is what it looks like asymptotically, and I'll prove it to you later. Well, now this is later, so that's the next thing we'll look at. But any questions about the partial wave expansion? Well, at this point, we will stop with the partial wave stuff for now. Again, if you think of it, again, I want to emphasize this is a very weird formula because the total scattering cross section is the total amount scattered everywhere. It's the total area seen by the incoming particle, no matter where it gets scattered, backwards, forwards, left, right, doesn't matter. And it's telling you that that whole thing is, you can figure out what that is entirely by looking at the scattering amplitude just along the forward direction and taking the imaginary part of it. It's weird. It's a weird theorem. But so it is. Okay, any questions? All right, so now we're going to move on to kind of general methods. I don't know what to call it. General scattering. Scattering in general. And again, the idea is we're kind of playing this trick where we know that actual scattering, what is it? It would involve taking, it's an intrinsically time-dependent phenomenon, right? If we were to do it properly, we would have some wave packet that we send in to some target, and the wave packet will interact with the target in here. And maybe it'll shift around the wave function and so on. And then eventually it'll come out, right, in some direction. And so this is intrinsically a time-dependent process. This is out at t minus infinity. Then we could say it interacts with the target at t equal to 0, and then we observe it at much later times using some detector. Say, oh, okay, we're going to detect particles here. So it's intrinsically a time-dependent thing, but in problems, we instead end up solving the time-independent Schrodinger equation and just looking at particular solutions that would correspond to this. And that's kind of the idea. But let's think about it more formally. And so what we do, of course, is sort of the time-independent version of scattering, where we just set up the right boundary conditions for a problem so that we can interpret the solutions as describing the scattering process. So what are the boundary conditions? Well, one, of course, is that you have a plane wave far away here, that you have an incoming plane wave, and you have some outgoing stuff. So that's kind of the sorts of boundary conditions that we're considering. You know, we can interpret those solutions as the scattering solutions. But actually, towards the end, maybe next class, I'll tell you why that's okay to approximate this, you know, time-dependent process as a stationary process. But we won't get to that for a while. So let's look at sort of the time-independent formulation. And again, the formulation involves just setting up the right boundary conditions to interpret those time-independent solutions as the scattering solution. And the basic thing we do, of course, is just solving the Schrodinger equation, which, you know, there's some potential we have, there's some H naught, which is, you know, the kinetic energy typically, and we look at some scattering solutions where E is our incoming energy, and psi plus is what we would call the scattering solution where stuff comes out. You send stuff in and stuff comes out. So if we were to solve this formally, right, what would we do? Well, we could have different scattering potentials. And so those can be complicated. And so what we would have a handle on, presumably, is this part, which is, you know, our kinetic energy operator. And so to solve this equation, what you might imagine doing, you can sort of rewrite it as follows. You can put the energy over here, and then you have, no, sorry, opposite sign here. You can put the H naught over here. You can put the psi plus over here. And then you could have some kind of equation for psi plus if we're able to invert this operator, which we might have some hope of doing because we know what the kinetic energy operator is.
What did I just tell you?
And so we might be able to get an equation like this. And then maybe we can have some iterative solution, perhaps, but we'll see. We'll see. So, but the idea is the first thing we want to get a handle on, because we don't know much, these potentials can be arbitrary. Again, so if you want to do the full solution, right, you would just have to figure out how to invert. This is an eigenvalue problem, so you'd have to figure out how to sort of diagonalize this whole thing. But suppose you don't, because you don't know what kind of scattering potential you have, then you can at least hope to get rid of this piece of the problem by sort of being able to invert the kinetic energy part. So that's kind of the hope of what, the hope here. And what's the idea? So we're going to try to understand this operator, which is the inverse of the operator E minus H naught. And its fundamental property as an inverse is that it in fact inverts this operator. So if we take the operator times its inverse and say we sandwich it between coordinate space eigenstates, then we know that this should just be the identity, and this reduces to a delta function of the coordinates. So this is where we'll sort of begin our analysis. We're going to try to figure out, can we actually derive what this operator is in position space representation? And this operator in position space representation is called a Green's function. And so let's look at it. So it has to satisfy basically this equation in position representation. So in position representation, any operator, of course, is going to have two indices, R and R prime. And this is the equation it has to obey in position space. So let's write our kinetic energy instead. We'll multiply through by 2m over h bar squared. So the Green's function equation will be the Laplacian kinetic, and then we'll have so this is minus h naught. This e is of course h bar squared k squared over 2m, but we're going to multiply through by 2m over h bar squared. So this, acting on the Green's function, you have to be careful with indices here. This is the Laplacian with respect to the first coordinate. If you think about these as sort of indices, you have to be careful how you do that. So this has to be equal to delta r minus r. So that's the equation that this supposed inverse operator satisfies. It's supposed to be the inverse of Laplacian plus k squared, which is just this operator. It's multiplied through by 2m over h bar squared. And so, but this is a differential equation that you could in principle solve. And well, I mean, this isn't really a PDE class, so the way we're going to solve it is just by guess and check. And of course, you want your Green's function to obey certain boundary conditions to make it relevant for scattering. So in particular, you can show that this equation is satisfied by the following functions. There's two of them, plus or minus, we'll call them. And they only depend on the they only depend on the difference between these two vectors. So I can write them as a function of, well, I don't know what to call it. We'll just call R. Well, it's just, I don't want to, it's going to introduce way too many primes, but okay, let me put this prime and this double prime, and then we'll define R vector as R prime minus R double prime. And so it only depends on the relative it kind of makes sense, right? Because the delta function only depends on the difference between the two. The solutions are 1 over 4 pi e to the plus or minus IKR divided by r. These are the solutions to that differential equation. And you can check that they work. So what you can do is you can just check the Laplacian, and you can act with it on one of these spherical waves, plus or minus IKR over R. You have to do a trick in order to do this properly. You have to add and subtract 1 over R, because I don't know if you remember from like undergrad E&M, the Laplacian of 1 over R is minus 4 pi the delta function. I don't know if you remember that. It's like one of the first things. I don't know, first thing. It's one of the things you do in that Griffith's E&M book. You can go back and look at that if you want to see how that works. But you have to add and subtract 1 over R to get this to work. So then we have, because the 1 over R is singular. This is singular, and that's why it gives you, it's singular at R equals 0. That's why it gives you something funny that's proportional to a delta function here. This function here now is nicely regularized, because as you send R to 0, this becomes 1 plus or minus IKR, right? And then minus 1. So it just becomes something that's proportional to R up here divided by R. So it's no longer singular. And in fact, you can write out the Laplacian in spherical coordinates and just do that derivative. Just do the derivative of this function. Remember, Laplacian, the spherical part is the one that depends on R looks like this. You can act with this guy on this function, and what you get is, well, unsurprisingly, because I told you the solution works, you get minus k squared e plus or minus IKR over R. So you get k squared multiplied, minus k squared multiplied by the spherical solution that we have. And then the other thing gives you a minus 4 pi delta R. So this formula is enough to show you that you can verify that if you take this function, act with it on these two things, you just get back out the delta function, because this plus k squared will cancel this k squared. So the k squareds cancel, and all you're left with is this delta function. This 4 pi cancels this 4 pi here. Then there's minus sign that cancels this minus sign. And you're done. I don't know. That's it. It satisfies this equation. So good. So those are the kind of fundamental inverse operators for the kinetic energy. They're written in terms of these spherical waves. So all right, that'll be helpful to us. Next, what we want to do, though, is look at what happens. So now we can actually go back to this equation and start thinking about it in. We can start thinking about it in terms of this Green's function. So let's do that. Let's convert this equation to in terms of coordinates. So if we do that, the relevant Schrodinger equation would be this acting on the wave function corresponding to scattering, which will be labeled with the incoming momentum. And to get the factors of h bar right, we get this guy, v psi of k. Plus, that's just the coordinate version of, and these are functions now. This is just the coordinate version of this equation here. This top one multiplied through by 2m over h bar squared. Okay. So, okay. And so now we see that psi of k plus is just equal to 2m over h bar squared times the inverse of this operator acting on v psi k plus. Now, the thing to notice is that, and this will be our Green's function. But before we write out what this is, so remember in position space when matrices multiply each other like this, you of course have to integrate because that's like a sum over indices. So we'll do that in a moment. But the thing to notice is that this operator, if it acts on a plane wave, then it gives us a 0, which is also something you can check. So I can add here, I can add to psi a plane wave, and it won't change anything because if you take this and act with it on any plane wave, you'll just get 0. You can check that. So I'm allowed to add a plane wave to this guy, and it won't change anything. So I can do that. I can add like a plane wave here, won't change anything. Let's put it in with a minus sign. So if I do that, and I do that inverse of that operator on both sides, I can just add here a plane wave. Why do we do this? Is because we have to introduce somehow remember the idea here was trying to find the scattering solution, which has the right boundary conditions. And one of them is that we have an incoming plane wave. So we're just manipulating things in such a way that we'll get an incoming plane wave plus something that has to do with the scattering. And you can always add an incoming plane wave in this formalism because this operator, well, you see here, because this operator acting on a plane wave is 0, we can add it here. Then we invert on both sides. We get this term. And then we can just add the plane wave here for free. And if I were to write this out in terms of the actual coordinates, you would get 2m over h bar squared. And remember, in coordinate, you can alternatively you can add in completeness relations in terms of the coordinates and so on. But the way I like to remember it is in a coordinate space, matrix multiplication means you sum over one of the indices, and that means you integrate. And now we have to use one of the Green's functions. So we know there's 2 of them. There's one that corresponds to an outgoing spherical wave and one that corresponds to an incoming spherical wave. So for the scattering solution, we really want an incoming plane wave and an outgoing spherical wave. So we would want to pick the Green's function that corresponds to that. So that's the right Green's function to use. Then, of course, it only depends on the difference between the 2 indices, and you sum over the second index as you would in matrix multiplication. Then the v, of course, is diagonal in coordinate representation. So this just looks like that. And of course, this is all acting on the wave function itself. So you can stick in a bunch of completeness relations and use the fact that v is diagonal and you'll just get this. But I'm going to skip all that because you should be relatively comfortable with that kind of thing already. You know, sticking in a bunch of you stick in a bunch of these guys, right? This. Okay, plus this guy. So now you see, and so this is exact. We haven't really done anything other than just rewrite Schrodinger equation in a very fancy way. But you see, by rewriting it in this way, we actually have a lot of, this is very close now to what we would expect the scattering solution to look like, right? We've got an incoming plane wave plus something, which is at least proportional to an outgoing spherical wave. Now it's kind of weird because we have the thing that we're looking for on both sides. But now you can imagine something like, suppose V vanishes, right? Say V is 0. This is gone. Then the solution is just the plane wave. That's perfectly reasonable. That's exactly what we want. If there's no scattering potential, then we want this guy to be equal to the incoming plane wave, right? So that's very good. And so then maybe we can have some hope of approximating this thing by doing a kind of iterative approach, right? Maybe we could say that if this term is small somehow compared to the plane wave, then we could replace this part with the plane wave, right? And we could, so the first order solution would be this equal to all this stuff times a plane wave instead of this guy right here. So we could do something like that, and we will. But this is basically a reformulation of the Schrodinger equation in such a way that it's more obviously connected to a scattering solution. And this has a name. It's called the Lippmann-Schwinger equation. And it's kind of like the basis to start with our analysis of scattering, the general analysis. Any questions about that? Okay, if not, then what we're going to do now is actually derive the asymptotic solution to scattering and really prove that it has that form that I told you about. It already is close to that. We have the incoming wave part. We have something that's related to spherical waves at least, but now we have this integral, which, well, I mean, it's a little bit different from what we had before. So we want to be able to extract the spherical wave part, and then maybe the leftover integration will have something to do with that scattering amplitude. Remember that the asymptotic solution, just to remind you, we're gonna try to connect this Lippmann-Schwinger thing to the asymptotic solution. I said that for large distances far away, this should be the incoming plane wave plus some scattering amplitude, and then an outgoing spherical wave like that. So we're going to see if this equation actually has within it something that looks like this, and then we'll be able to identify the scattering amplitude. To do that, you have to figure out what happens at large distances. And so the first thing to do is to look at this Green's function at large distances. And if we write this out, you get the -1 over 4 pi. You've got the e to the I k r, and now we're gonna write the so this is the magnitude of the difference between r and r prime. And so this we can write as r hat minus r vector prime over r. Just rewriting it. And this is over r, and this is magnitude r hat minus r vector prime over r. Now let's think about this. What is this r prime? The r prime is our variable of integration here. And r prime is going to really, this integral is going to only contribute stuff when v is non-zero. And so the r primes kind of live, live in the vicinity of the target. And the r's we're going to take as somewhere far away where we're looking, somewhere quite far away from the target. So that means we'll be able to say that the magnitude of r prime is going to be much less than the magnitude of r. So we can Taylor series expand in r vector prime over r. This is going to be small in magnitude. It's going to be a small vector. So this is equal to minus 1 over 4 pi e to the I k r. And then we just pick the first two terms in the Taylor series. The first one is just 1. And then you have a minus r hat dotted into r vector prime over r. And then there's other stuff that's of order 1 over r squared. And that's going to be small. And down here we have r 1 minus r vector dotted into r prime over r, and again plus higher order terms just go like 1 over r squared. Okay, so good. And now in principle, we could approximate further. So we dropped all these terms, and now we're going to drop this term. But we should still keep around the term that's in here, because this could actually still contribute quite a bit to the integration because it's in this phase, and k could be, and well, I mean, we have to keep it because it'll still contribute to the integration due to this oscillating exponential. But this term will be kind of subleading relative to this 1 over r piece. I think you could probably work out the next, you could probably go out. So you can go out to higher orders, of course, and see what happens. But to a good approximation, this inside the integral is just minus 1 over 4 pi r e to the I k r times that leftover exponential, which is e to the minus. Now the r's cancel, and it's I k r hat dotted into r prime. So you'll see that this contributes, right? Because you still have to integrate over this phase. So this will still be significant, as opposed to this term, which just gives you a kind of 1 over r, an extra factor of 1 over r, proportional to another factor of 1 over r. So that's not going to. Yeah, that actually won't contribute. But I have to think. I guess I myself sort of think this makes sense, but maybe there's a stronger justification for why you can drop this term. I'll have to think about that a bit. But in any case, we'll drop it and see what happens. So plugging this into here, we get that the solution now is incoming plane wave, and now we have a minus m over 2 pi h bar squared. That's just that minus 1 over 4 pi bit. We have the e to the ikr over r. So yeah, I guess maybe this is the other way to justify it. You can keep these other terms, but it would give you something that doesn't have a 1 over r in it. And I guess you could keep that and see what happens with it. But yeah, I don't know. Again, something to think about. Maybe you guys can think about it too. But so we at least have the outgoing spherical part. That's what we wanted. And what we're left with is an integration over r prime of e to the minus ik r hat dotted into r vector prime. And we have our v of r prime times the psi k plus of r prime. Now look, this is great because, well, we have everything we need. This has exactly the right form, right? We have the e to the ikr over r. We have the incoming plane wave. So everything else out here must be the scattering amplitude. Must be all this stuff out here. So that's very cool because we can now start approximating the scattering amplitude. So it's minus m over 2 pi h bar squared. We've got the, so yeah, this is a funny vector. K times r hat is like, it's the direction you're looking at, and the magnitude of it is the magnitude of the incoming wave vector. But it's not the same as the k vector. It's something that often confuses people, that, you know, this isn't the same as the k vector. This is magnitude of k times r hat, and r hat is the direction you're looking at. So it's the direction, it's this direction of the place where you're looking. So something to keep in mind. Then you got the v of r prime. And now we can, of course, instead of putting this guy, we can do what I said and do the recursive thing, and instead put in e to the I k dot r, right? We could put in this part if like v is small in a sense, and if we look at the first, if we look at the solution to this equation recursively, you put this in, and now this is nothing but what's called the Born approximation, which you derived on the homework using a completely different way. This is e to the minus I, and all this is, so now we have to be careful. We can drop the prime on this r vector, and k r hat, again, this is the magnitude of k times the direction you're looking at. So indeed, k r hat is nothing but the sort of outgoing wave vector. Because remember, in an elastic scattering process, the magnitude of the k's is the same. And so the only, what k prime is just the direction you're looking, the way in which things are scattered, times the magnitude of k. So, and now we can drop this prime, because this is just a dummy variable after all. We can drop this prime, and we get integral ddr minus I, and this becomes k prime minus k from this part dotted into R. I should put prime here. So now that we drop the primes on the R's, and this becomes V of R. And that's it. This is the Born approximation, which you guys derived in a completely different way. And well, I don't know, that's pretty great because moreover, now you could actually start thinking about how you do corrections to this. So instead of keeping just this term, you could keep, you could do it recursively and start keeping this plus this, where this is replaced with a plane wave. And you can do that. And we'll do that now, but we won't use these awkward coordinates. We're going to use the operator notation. And that'll be really nice. And so we'll see. Okay. Any questions, though, about that? Or what we did here? Again, we rewrote the Schrodinger equation to this form, which looks an awful lot like scattering. Then we looked at what happens to this Green's function far away. And if you believe that far away, this green function looks like that, which it does, and you have to worry a little bit about, which terms in the Taylor series you can draw. But if you believe this part, then you immediately conclude from that the Lippmann-Schwinger equation far away looks like this. And then if you interpret this as a kind of iterative solution for psi, where the first order term is the plane wave, you plug in the plane wave here, then you just get the Born approximation for the scattering amplitude. But already at this stage, we see that it's true that asymptotically, the solution of the Schrodinger equation has this form: incoming plane wave plus something, which is this circled thing over here, times this outgoing spherical wave. So at least we proved that. But okay, so now we can move on to doing to studying this in a more operator language. And one of the things that we'll show in a little bit, so remember that this G plus or minus is supposed to be, equal to the inverse of E minus H naught. But there's a subtlety here, right? In that it's unclear how you pick out the plus or minus, right? One of them is the outgoing spherical wave, one of them is the incoming, and there's nothing in this operator notation that'll tell you which one it is. And as it turns out, and I'll show you this to you next class, the way you pick them out is by introducing a small imaginary part to this denominator, which you then send to 0. But depending on how you send it to 0, either from positive values or from negative values, you'll pick up either the plus solution or the minus solution. But I'll show you that later. For now, I just have to take my word for it that that's how it works. And so then the Lippmann-Schwinger equation in terms of operators is incoming plane wave plus G plus acting on V psi plus K. So that's Lippmann-Schwinger and operator notation. And in operator notation, it's much easier to understand how to get the iterative solution, right? So if we were to solve this equation iteratively, we would just keep back substituting in. And I guess I'll have to stop there though, because we are indeed out of time. But let me just box this for now, and I'll box it in the same color as I'm about to box the Lippmann-Schwinger equation, which is, where is it? Yeah, it's up here. Yeah, there's an extra factor of 2m over h bar squared, which I keep forgetting about. But okay, we could, okay, but it's this equation actually, because I didn't put the G. So this is, it's not, yeah, it's, 2m over h bar squared times g, I guess. Yeah. So anyway, this is the Lippmann-Schwinger equation in operator notation. It's the same as this equation in coordinate space. So I'll leave you with that, and then next time what we'll do is we'll solve this guy iteratively and give you the Born series where you can take the Born approximation, make it, get arbitrary corrections to it. But yeah, that's it for now. Any last minute questions about anything?